Good afternoon. Back in the old days, about 2007, I remember coming to a much smaller TCT conference than this, and the talk at the time was really all about how the industrial paradigm was changing from mass production into mass customization, and the future of manufacturing was going to really be based around 3D printing as a technology. 7 years later, the terminology's changed again. We now have 3D printing, but the industrial paradigm hasn't changed that much. We still have mass production well in charge. Mass customization is coming in, and it's improving very rapidly. Companies like Makey Labs are really, I think, showing the way to the way that mass customization can be implemented in a very positive and very creative way. They have fantastic online design software and the ability to customize the design of the doll that you want them to make to an almost limitless degree. It's extremely well done, and the models themselves are improving very rapidly. So I think Makey Labs are a fantastic example of how mass customization can work. And you can see some of their models on the 3T stand here. There have also been, I think, some incredibly positive developments in the world of 3D printing generally, more conventional 3D printing, if you like. I think the eNable project, which I've recently come across, is a passionate network of volunteers who are designing, making, and fitting prosthetic limbs using standard 3D printing devices, specifically FDM machines. And this is now becoming really a global network of people who are, I guess, in a way, showing what you can do when design and manufacture is democratized. It's really putting manufacturing of these rather specialist devices in the control of people who can make them in their own homes and provide them for people in their own village. And it's a much more positive vision of 3D printing than the hysteria that we often hear about 3D printed guns, for example. But whether you're printing prosthetic devices or Formula One parts or medical devices, the vast majority of 3D printed parts are still one-off components. And the trend towards domestic 3D printing, if you like, personal 3D printing, really only seeks to sort of enhance and develop that trend. But what I want to try and look at today is what happens if you've got a design that can only be made using 3D printing. It can't be made using conventional manufacturing techniques because it's got undercuts, it's got re-entrant features, it's got a whole load of complicated things that would make it unsuitable for conventional manufacture. But you don't want to make 5 of them or 10 of them, you want to make 100 or 2,000 of them. Conventional 3D printing wisdom would really say that there isn't a problem. You just keep making more of them, and you keep churning them out, and you modify them if you need to, and you just keep making more parts. But the issue I have with that is that when you actually talk about using 3D printing technology for manufacture, as opposed to making one-offs or prototypes, some really quite significant issues begin to come into play that don't really apply at the one-off level. And the first of these are our old friends time and money. It strikes me as strange that you never hear people talk about the cost effectiveness of 3D printing. We talk about the technology, what it can do, the amazing things we can make, but it's very rare, if ever, that you come across people saying whether it's affordable, whether it's economic. And the reality is that in many ways it's not. The materials are very expensive compared to conventional materials. The machines themselves aren't cheap. And although all this is getting much better and it will get better very quickly, it is still quite an expensive process, and it does still take quite a lot of time. Another issue that rarely gets mentioned is that it's also quite a wasteful technology in many ways. All 3D printing technologies are, to a greater or lesser extent, quite wasteful. You've only got to look at the electricity bill of anybody who's got a direct metal laser sintering machine to realize that it uses a tremendous amount of energy. And although most other processors don't use anything like the energy that a DMLS machine would use, it's still quite an energy-intensive process. The materials themselves very often aren't recyclable, which is odd in these days when we consider everything should be recyclable. So there are issues to do with the environmental credentials of quite a few 3D printing processes. And finally, there's the whole question of finish, quality, and fitness for purpose. Do the materials that we want to use, are they suitable for manufacture? Not as a personal device that we might use at home, but are they suitable for something that we want to sell to somebody else? Will it last? What will its material behavior be like in 5-10 years' time? Will it become brittle? All of these things are issues that affect the manufacturing use of 3D printing far more than they would affect a personal 3D print or a prototype. So these are just some of, I think, the issues that we need to consider when we're transitioning between prototype level, one-offs, and manufactured products in a large scale. We also need to consider the whole issue of which machinery is suitable for the purpose that we're trying to use it for. And again, this is really very much a moving target. The technologies are developing very rapidly, as we can see from everything that's here today. But at the moment, many of the systems that are used for 3D printing aren't particularly appropriate for manufacture because they were designed to make one-offs, often in materials which won't necessarily last a very long time. And so we need to be a little bit selective about which are the best systems to use for a manufacturing process. And at the moment, the main ones that are really at the forefront, although this isn't by no means an exhaustive list, but the main ones really are selective laser sintering, SLS, which gives a very sound mechanical result. The metal sintering processes like direct metal laser sintering or DMLS, and FDM, which does provide ABS or other conventional engineering plastic parts, which can be used, I think, in a manufacturing context. The other side of this is the materials themselves. There's a huge range of materials now coming into use, and it's growing all the time. Very often these have exactly the same fundamental material properties as their, if you like, injection molded or mass production counterparts. The difference is that we have to consider how they're made and the process by which the material is laid down, because very often, for example, on an FDM machine, the layering structure won't give you the same material properties or structural properties than, say, an equivalent injection molding would have. So these are all issues that we need to consider. They're not problems, they are just simply differences that we need to consider when moving from prototype to production. But from a design perspective, what do we need to consider? Well, the first one is, will it fit? We've seen this discussed quite a bit. It's an interesting conundrum about 3D printing where we're told we can do anything we like, that one of the basic limitations is the size of the build chamber in which we're working. Again, these are growing, they're getting much quicker, very quickly, but they're still limited, and we need to consider that. We can, of course, always join parts together. This is a prototype front end for a smart car, which is made of several pieces of SLS bonded and joined together. But again, we need to consider cost, and we need to consider the cost of finishing and assembly. Another issue that relates to the build chamber is the question of part strength. Most 3D printing processes will give us parts which are anisotropic. I had to make sure I got that right. Or basically very similar to wood. They're going to be stronger in one direction than in another. So for many layer-based systems, we need to make sure that a very thin part like this is built, in effect, lying down, where the layers run longitudinally through the part, rather than across it at its thinnest point, where it will become very brittle. Similarly, and again, this is sort of more a general comment than a specific one to any particular process, we have to consider things like wall sections, which very rarely go down below 1 millimeter. We have to consider things like the plane in which you would put a fine feature, like a piece of text or a small hole, which would normally be parallel to the build direction to keep it clean and neat. And there's also the issue of thick and thin sections, which again is a bit of a fundamental design issue. A lot of people would say that it doesn't matter putting thick and thin sections together in a 3D printed component. I would beg to differ for two reasons. One is, if you're using something like SLS, the high temperature buildup you would get in the thick section might distort the thin section next to it when the part cools down. And the second reason is just good old-fashioned engineering. Why have a thick section if you don't need it? It's wasting material, it's using extra processing time. So unless there's a good reason for having thick sections in a part, I don't see any point in using them. So there are these really quite fundamental, basic design decisions that need to be thought about. And then also there is the question of the economic viability of the build process. With some processes where we're dealing with a build platform, you're quite limited as to how many parts you can get on the build, and you have to nest them quite carefully together on a single build platform. With processes like SLS, you can in effect fill the entire build chamber, and it becomes a 3D jigsaw puzzle of parts. And so the individual economics of the parts can be much greater. So these are just some of the general considerations that we need to, I think about when we're looking at using 3D printing as a production process and looking at the different systems and how they work and how they can be used efficiently. We've been talking just now, I think, about nesting parts one inside the other, and I think this design, Freedom of Creation's Lily lamp, which is one of the earliest examples of 3D printed manufacture, and I think still one of the best, shows, I think, a very creative approach to cost efficiency. The designer of this very cleverly nested the smaller version inside the bigger one, so that the manufacturer of these parts quite literally gets two for the price of one. And when you finish the build, you simply have to extract the smaller lamp from inside the bigger one, and you've got two parts instead of just one. So it makes a very efficient use of the build chamber itself. And I think this kind of creative approach to design, applied to the economic side of it, I think is a very useful example of how 3D printing design can be well adapted. Sticking with the Lily lamp and talking about finish for a moment, we've just been talking, I think, about how 3D printed parts are finished and the way in which we can get a good and acceptable surface finish on them. Freedom of Creation have always taken the view with many of their parts that they supply it as a natural, if you like, finished SLS part. It's got quite a granular structure on it, quite a granular surface. Beautiful when it's first made, becomes a bit of a dirt magnet about 2 weeks later, but to begin with, it's a beautiful surface to look at and play with. More recently, people have started to develop much better systems of finishing the parts, both in terms of getting a smoother surface, but also applying colour to 3D printed components. These range from tumbling machines, which if any of you ever did lapidary as a schoolboy or girl, you would know from sort of tumbling rocks inside a drum that polishes things. It's a fairly simple technology, but it's being applied very successfully to some 3D printed parts. FDM parts could be put into a vapor chamber where the surface is just very slightly melted to give it a more shiny surface. And there are a whole range of other technologies coming in now, which I think offer the possibility of, if you like, mass production level commercial finishing technologies for 3D printing. It still remains the Achilles heel of the whole industry in many ways, because it's usually very difficult, time consuming and expensive to finish a 3D printed part to the same level of surface finish that, say, an injection molded part would have. And very often it can double the price of the component. But actually, just this morning, I was talking to somebody from one of the companies here who was saying that they've just been developing a new system that can produce a beautiful polished surface on almost any 3D printed component, and it costs pennies per unit. So again, like the rest of it, it's moving quite fast, and the technology really is developing quite quickly to the point where we will have affordable methods of reasonable batch or mass production volume 3D printed components that can be finished to a very high standard. One of the main issues, I think, that faces designers when they're using 3D printing for manufacture is the question of predictability and repeatability. It would be nice to think that all the technology that's involved in these processes we're looking at today would guarantee that every part you make is the same, everything comes out precisely the same every time you make it. But sadly, it's not the case. Again, talking to one of the biggest suppliers here this morning, we were discussing exactly this, and the whole issue of material suitability across a consistent range, the fact that lasers will go out of calibration, the ambient temperature of a build chamber can sometimes affect the way that part is built. A whole raft of issues can make very, very small changes, but if your product depends on an absolute precise copy every time, then some processes won't necessarily be able to deliver that. Now, That's not necessarily a problem, provided that we design around it or with it. And I think that's really one of my main points I want to try and get across today, is that what we, I think, need to do as designers is to understand the processes well enough that we know how to work around some of the issues that all of these processes have. We addressed this kind of problem very much when we were working with Makey Labs on their 3D printed dolls a couple of years ago. The joints on the dolls are designed to be articulated like any doll or marionette, and their initial designs were based on conventional injection molded toys like Lego, where the joins were a tight snap fit. However, what they found after a few weeks of use was that the joints started to become quite floppy as the thing was used by the customers. They asked us to look at this from a design point of view and find solutions to the problem. And initially we followed their route and looked at different types of mechanical joint with greater degrees of friction, greater degrees of pressure. But the same thing happened. After a small amount of use, the parts polished each other and they began to wear loose. And what we realized was that there was an issue here of variability within the parts, partly in the build process, but also in the way that they were used, and that we needed to provide some means of adapting to that. And the solution, which we came up with, because we didn't want to change anything fundamentally, the design was already in pre-production, was to simply hollow out the limbs, in effect, and which reduced the weight in the material anyway, and then introduce a silicon rubber spring, just literally just a short cylinder of silicon rubber that was pushed into the joint and provided some pressure on the actual pivot point of the joint itself. This pretty simple solution provided the answer, because it meant that the friction in the joint that kept it where it was supposed to be wasn't down to the mechanics of the SLS part, it was down to another component that was actually providing friction and pressure to keep it where it was supposed to be. And I think I'm just putting this really in as an example to show that if we really work around the issues, and let's face it, every process, whether it's injection molding, sheet metal, or 3D printing, every process has its limits. If we work around those limits and understand what they are, then we can find solutions that retain the best qualities of the process, but actually address some of the shortcomings that it does have. This kind of approach, if you like, is particularly true of support structures. We've just been hearing about support structures using SLA type machines, but in some systems, particularly if we're looking at direct metal laser sintering, particularly because it's an expensive, time-consuming process, but other processes as well, any downward-facing horizontal surface is going to require support during the build process, either because the material is molten, as in the case of metal sintering, when it's built, or it's just soft and can't support itself. So very often, when we're using any part that's got a downward-facing surface, it's got to have a support structure. There are two really fundamental problems with this. One is we've got to build it in the first place, which uses power and time, and then we've got to remove it, which uses more power and more time. And especially with metal sintered parts, those are quite significant lengths of time and power. So anything that we can do that minimises or removes those kind of supports is going to save money, and that again, in a manufacturing context, is going to be particularly important. From a design point of view, most processes, obviously this doesn't go for every single one, but most processes can avoid some or all of the build support structures that it would otherwise need if the design has either angles in it, somewhere between 30 and 90, but some metals, for example, in DMLS will build at 30 degrees to the horizontal. Others will require a sharper degree of angle. It gives you a stepped surface, it gives you a slightly messy surface, but at least it doesn't require complete machining to remove the support structure. And similarly, putting a circular hole in a part can allow the part to build up around the hoop, around the circle, without necessarily needing supports. Again, without getting too specific about it, those holes need to be fairly small, but a circular hole can be built without support structures in many systems. The standard sort of bicycle rat trap pedal Normally something that's made of fabrications and forgings or or castings, but if we imagine that as a metal sintered part for a moment, built horizontally to the build platform in the way it's shown here. If that is built using a process like DMLS, it's going to require this level of support during the build process. There's a lot of downward-facing horizontal surfaces there that need to be supported as the part is built up, and all of those would then need to be removed and machined away. So the effect of that on the cost of the part is obviously going to be quite considerable. If we turn the part to 90 degrees and we play around with the design a bit, introducing a few angles and a few angled surfaces to minimize the amount of supports we need, then the amount of support required is quite significantly reduced. And again, I think this just underlines the importance of getting the orientation of the part right in a particular build process. So that's a much better way of doing it, but that's still sticking with the conventional bicycle rat trap pedal design. If we throw that away and start from first principles, working with the process and working out what it can do, what the benefits of the in this case, direct metal laser sintering process is, then we can do a number of things. First of all, we can do away with support structures completely, because there are no downward-facing horizontal surfaces in that part at all. Secondly, we can, and this is getting a bit detailed, but secondly, we can make it more efficient during the build process itself, because the small holes mean that as the layers are built up, the geometry is self-supporting. If you imagine something building up with two very long, thin strands in it that will eventually be joined, 3/4 of the way up those long, thin strands, they're going to be fairly weak. So peppering something with holes means that as it builds up layer by layer, the part retains its structural integrity as it goes upwards. And all this then requires is wire erosion cutting from the build platform, and you've more or less got the finished part. The point with this is that if we start with an understanding of how the process works and work with it, we can actually create new designs which don't depend or reference the old designs we used to work with. We can create entirely new designs, which in many cases can be very radical and very exciting, but we can also work with the strengths of the technology rather than trying to force it to do things it doesn't want to do and become more expensive. And the final benefit of this is that certainly from a build construction point of view, you can get an awful lot of them on a build platform. So each build cycle enables you to build a lot of parts at one time, which obviously significantly reduces the individual cost of each part compared to just doing them as one-offs. So this kind of approach, I think, has a lot to be said for it in terms of using 3D printing for manufacture. So in conclusion, I've just got 3 points to make, really. The first one is that, as we so often read in design magazines and even in The Economist, we can forget most conventional design rules when it comes to using 3D printing. Sure, we don't need to worry about undercuts, we don't need to worry about draft angles, it's fine. But it's a mistake, and I think quite a big one, to assume that that means there are no design rules at all. There are design rules with 3D printing, they're different, and they're different for each of the technologies that are on display in the hall here today. But getting to know them will help us design better products. And the second thing is to understand those processes and understand the processes that we're working with to make the most of them. I think it's the popular idea that we can do anything we like with 3D printing, that the design is only limited by your imagination, is frankly fairly lazy thinking. You can do anything you like with 3D printing, but at the end of the day, you can do anything you like with a hammer and a chisel and a very large block of wood. It's a case of, is it economic? Does it work? Does it make sense? And if we want to make the most efficient use of the systems, we need to understand how they work. And then finally, from a design point of view, I think we can work with these, if we can work with these processes, we can actually create new designs, exciting new designs that don't reference traditional methods and traditional ideas, but make the most use of the technology that we've got. Fortunately, we've got some quite useful ideas around these days to help us do that. This book's recently been published by Douglas Bryden from Edinburgh College of Art. I can thoroughly recommend this book. It's an excellent summary, I think, of all the different 3D printing processes that are around at the moment. And it's got some fantastic examples in it of how designers are using those processes to create new and very exciting ideas and designs. So I think it's very well worth having a look at this if you're thinking of finding out more about the individual processes that 3D printing comprises of. And not entirely surprisingly, we've got one of our own, which is a white paper that we've just published, which is we call it a basic design guide to 3D printing. In this, what we're trying to do is to look at the main processes that can be used for manufacture and look at some of the design issues in a lot more detail than we've had time to look at today, in terms of the finer points of wall thicknesses and so on. It's a PDF download off the website. It's entirely free. We've literally just published it this week. So if you do download a copy and have a look at it, I'd be very grateful for any comments you've got. Thank you very much.